So a linked list is kind of the first serious data structure you learn about, because it's very simple and it's actually got a structure. I mean, an array's got a bit of structure, but a linked list is kind of slightly more complex. We can do some more interesting things with a linked list. So a linked list is made up of nodes. Each node stores an item of data, so it could be a number, it will be in our example, because it's easy to write, and it has a reference to the next node in the list. If we wanted to store the numbers 1, 2, 3 and 4 in a linked list, it would look something like this. Each node stores a value and a pointer to the next node. So the value is 1, then we have another node with 2 in it, and the first one points at the second one. And then if we want to have 3, we can add that.
Where do you put the link? Is it in the new thing, or is it...
No, if you're adding things at the end of the list, the link goes from the existing node to the new node. If you're adding things at the start of the list, which you can do, which you can't do with an array, because where do you put it? You've got nothing, you don't have access to what's before that in memory. You know, you're going to trample over something else and cause problems. If you want to add a node at the start of the linked list, say you wanted to add 0 to this list, we could just create a new node somewhere. It doesn't matter where in memory it actually is. They don't need to be next to each other. These arrows can just point to anywhere else in memory. So if we wanted to add the node 0 to the start of this list, we'd create a new node, put 0 in it, and then point it at this element. So in a linked list we have 2 special nodes. We have one called the head and one called the tail. So the head is the node at the start of the list that points to everything else. The tail is the node at the end of the list that is pointed to by the previous node and points to nowhere. In general, with a linked list you need to keep track of at least the head. The tail is kind of optional. You don't have to keep track of the tail necessarily. So this node is going to be the head of our linked list. So we'll have some reference somewhere, probably a variable called head that points to this node. So if we want to find things in the list, we can go to the head and then we look at its next pointer, and this one's next pointer, and this one's next pointer. The last element in a linked list, the tail of the list, you'll notice this doesn't point anywhere. Conceptually, there needs to be some value here. We can't leave it as uninitialized memory because it will be an arbitrary number. It will point to somewhere, who knows where in memory. And if you follow that link and try and interpret it as a node, you're probably going to make your program crash. What we do is we point it at null. So in C or Java, it's called null, or it'll be the number 0, like a memory address 0, which is interpreted as null. Or in Python, it would be none. I think it's null in most languages. If our node points to null, then we know it's the last item in the list, which is nice. We know when we've gone through the whole list and found every element.
Kind of reminds me a little bit of a sort of treasure trail where you find something and then it tells you where to go next.
Yeah, I guess it is like that. So, yeah, I mean, similarly to that, you can't find a middle clue without having to find the one before it. So with a linked list, you don't have random access or constant time random access to the elements. So if you wanted to find the last but one element in the list, you need to start from the start, keep counting forwards, probably until you get to the last one, and then, oh, it was the one before that. I mean, if you want to get to the 10th element, you have to go through 10 times. So in an array, you can access the 10th element really easily. You just say, get me element 10, it multiplies the width of the variable, or the width of the item by 10 and jumps that far in memory. With a linked list, you can't do that because they're stored in arbitrary places in memory, you don't really know where, and you can only get to them by following the links. So if it's the 10th thing, you've got to follow 10 links. If it's the 1000th thing, you've got to follow 1000 links.
Because they could be buried anywhere in however many gigabytes of RAM on your computer, is that right?
Yeah, these could be anywhere in memory, you could be jumping around all over the place. Yeah, that's the only way to get there is to follow the links. Sometimes we might also want to maintain a reference to the tail as well as the head, so we can just point tail at this last element, and this helps us if we want to add elements to the end of the linked list, because if we know where this node is, we can stop it pointing at null and point it at a new node, and then point the new node at null.
What happens if you need to add something in the middle of a list?
Well, let's say we wanted to add the number 26 in between 1 and 2. Just, who knows why, but we want to do it. So what we need to do is create a new node somewhere. It doesn't matter, let's put it here. That contains the number 26. We need to break this link, so that's no longer there, and we add 2 new ones, one for pointing from the node 1 to 26, and the one pointing from node 26 to 2. If we wanted to do this in an array, what we'd have to do is we'd have to shift every element after 1, down 1. That would take n operations, and then put the number 26 in the gap we just made by moving the 2 along. So with a linked list, after we found the place we want to insert the nodes, it's constant time insertion, because we're breaking 1 link and creating 2 more. And that doesn't matter how many nodes there are in the list, we're changing 3 links, breaking 1, adding 2. Searching may take up to, if we want to insert after an element with a value of 3, we're going to have to search through the whole list, and that will take up to n, so up to the number of things in the list. The actual insertion is constant time. Also, if you want to remove an element from the list, that's quite easy too. What we would do, we'd break these 2 links, and then we create a new link, joining 1 to 2 again. There's a slight special case for inserting and removing. If you want to do it at the head or the tail, you need to change the head or tail reference to point to the new node that is the head or tail. So if we wanted to remove the first node in the list, we would break this link, we would break this link, and then we would create a new link from head to the new head of the list. Similarly, if we insert, we'd point the head at the new node. If we delete the tail, we point tail at that node. Create a new one, we point it at the new node. These linked lists we've looked at so far are called singly linked lists because they each have a single link to the next node in the list. Now, there are also doubly linked lists. So a doubly linked list has a link both to the next node and the previous node. The nodes look slightly different. They now have 3 compartments, I guess. So we have the value still here. So we've got 0, 1, 2, 3. Each of these has a pointer both to the next node and to the previous node. So next, previous, and of course, not forgetting, that goes to null, and that goes to null. So you can kind of think it's a breadcrumb trail, but it goes both ways. So if you want to, you can start at the head and go down to the tail, or you can start at the tail and work your way up to the head. Still, you don't have very good random access because you've either got to go from the tail and backwards, or from the head and forwards. Okay, so a practical example of where I've actually used a doubly linked list in almost the real world. In your web browser, you visit a website, you click some links, you go to a next page and a next page and a next page. And then in the top corner, you can click the back button and go back a bit, and keep going back. But you can go forwards again. And then also, you might go back a bit, you might click another link. Let's see how this works as a linked list. I'm just going to draw the data compartment because it's easier. So we start with main page. At the start of the list, this points to null. This will also point to null. As soon as we browse to somewhere, so yesterday I was looking up on Wikipedia, there was a link to NASA on the front page, so I went to look at NASA. So this points back to here, this points to null, because we're browsing NASA. And then read a bit about NASA, clicked on the Neil Armstrong article. This points back here and points forward to null, because it's the end of the list. From Neil Armstrong, I started reading about Apollo 11, so points back to Neil Armstrong and forward to null. So while we're going forwards, we know which page we're on, so we're on Apollo 11. So we're pointing at Apollo 11 here. Here's my hastily constructed non-blow-awayable pointer. So I think enough about Apollo 11. I'm going to go back a couple. So let's go back to Neil Armstrong. Now we're reading about Neil Armstrong again. So we're on his page. If you want to, we can go forward to Apollo 11, click the forward button. But okay, we go back a couple, back to NASA. Our back history is still there, our forward history is still there. However, we decided to click another link on NASA. We decided to look at the International Space Station page. So there's a link from NASA to the ISS page. So we click this. Now, we break this link. We no longer have Neil Armstrong in our forward history. We're now at ISS, pointing back to NASA. And if we go back to NASA from ISS, we're at ISS and we go back to NASA. We can't get back to Neil Armstrong anymore. We have no way to get there. Every time we're on a page and we click a new hyperlink, we break the previous history, the previous forward history goes away, and we create a new node that represents the current page we're on.
Are there any other things that this sort of code gets used for?
Yeah, so you might do this with something like undo and redo history in a program like Word or Notepad or something like that. Some sort of editor. Every time you click undo, you go back to previous states, but your redo state is still there until you do something, and then you've lost all your redo history. Unless you're using something like Vim, which I think stores all your undo and redos as a tree, and you can eventually get back to the things, so it doesn't ever throw anything away.
But for most ones, would you say it's breaking the chain?
Yeah, so you break the chain, you throw away all this future that you've gone back from, and it's gone. to look at the names and make the names meaningful. So instead of doing that, you can use a thing called an array, which is one name that points to multiple items of data, which we store next to each other in a contiguous block of memory.